We watched a dim star flicker, and a tiny dip hinted at something larger, perhaps a planet that might hold water. The Kepler spacecraft, launched in 2009, sat silently at the Sun-Earth L2 point, its photometer staring at a fixed patch of sky. Its purpose was simple: count photons, watch for the faint, regular dimming that a planet imposes as it passes in front of its star. The method, called transit photometry, is patient work. One must trust that a small shadow, lasting only a few hours, is not a glitch in the detector but a real body crossing a distant sun. Kepler's first data release revealed dozens of candidates, each a tiny notch in a light curve. Most of those were close-in planets, scorching under their stars. The community was still learning how to separate noise from signal, how to confirm that a dip meant a planet at all. In that early period, every new detection felt like a tentative step. Then, in early 2011, a pattern emerged from the star designated KIC 10,593,626. The light curve showed a dip every 290 days, each about 0.5% deep. That depth corresponds to a body roughly 2.4 times Earth's radius, large enough to be called a super-Earth, but small enough to avoid the gas giant regime. The orbital period placed the planet squarely within the region where liquid water could exist on a rocky surface, the so-called habitable zone. The announcement that Kepler 22b was the first confirmed planet residing in such a zone was more than a headline. It marked a shift from cataloging hot, barren worlds to actually looking for places that might share Earth's temperate conditions. The detection proved that Kepler's instrument could reach out to a star 600 light-years away and still resolve a signal the size of a human hand against a distant lantern. 600 light-years is not a distance we can imagine walking to. Light, the fastest thing we know, takes 6 centuries to travel that span. For an observer on Earth, the photons that formed the dip left the star long before we even built telescopes. The fact that we can still read that ancient flicker feels almost absurd. I find it hard to picture a star's surface moving in lockstep with a planet we have never seen. At the time, the planet's mass remained unknown. The transit method tells us size, not weight. Without a radial velocity measurement, we could only guess at composition. Was Kepler 22b a rocky super-Earth cloaked in a thick atmosphere? Or a mini Neptune with a deep envelope of hydrogen and helium? The data left both possibilities open. This uncertainty reminded us that a single detection is rarely a full picture. Historically, the first exoplanet around a sun-like star, 51 Pegasi b, was announced in 1995. It was a hot Jupiter, a gas giant skimming its star in a few days. That discovery shocked the community, because it broke the expectation that planetary systems would look like ours. Over the next decade, the tally of known exoplanets grew, but most were still far from the temperate zone. Kepler 22b arrived as a quiet counterpoint to those early hot worlds, suggesting that the galaxy might host a variety of orbital arrangements, some more Earth-like than others. The detection process itself required careful verification. Kepler's pipeline flagged the signal, then a team of astronomers applied a suite of statistical tests. They checked for secondary eclipses, for variations that could indicate a binary star masquerading as a planet. They examined the star's own variability, ensuring the dip was not caused by stellar spots. After weeks of cross-checking, the consensus was that the signal was best explained by a planet. Even with that consensus, the community remained cautious. We don't really know how thick the atmosphere might be or whether the planet's surface is solid at all. The habitability label, while useful, can be misleading if taken as a guarantee of life. The term merely denotes that the planet receives enough stellar energy for water to exist, assuming a suitable atmosphere. That assumption is the biggest unknown. Kepler 22b also highlighted the limits of our instruments. At 600 light-years, the star is faint, making precise radial velocity follow-up difficult with current spectrographs. The planet's mass could remain ambiguous for years, perhaps forever, unless a future mission with higher sensitivity targets it directly. The lesson was clear. Detection is only the first step. Characterization often lags behind. In the broader picture, the discovery reinforced the design philosophy of the Kepler mission. Monitor many stars continuously, let the statistics speak. By observing over 150,000 stars, Kepler could find the rare alignment that produces a transit. The success of Kepler 22b gave confidence that, with enough eyes on the sky, the odds of catching a temperate planet improve. It also motivated the planning of successor missions, like TESS, which would scan brighter, nearer stars. The story of Kepler 22b is, at its core, a story of patience and small signals. A dimming of a fraction of a percent, repeated once every 10 months, survived the noise of cosmic rays, instrumental drift, and stellar activity. That persistence is what allowed astronomers to claim a new class of planet, a super-Earth that might sit in a temperate orbit. Even now, the data set still holds subtle clues. Some researchers have noted a slight asymmetry in the transit shape, hinting at possible atmospheric scattering. Others have pointed out a faint secondary dip that could be reflected light, but the signal sits at the edge of detectability. I don't quite make sense of those hints when I read them aloud. They feel like whispers lost in a crowded room. What remains striking is the simplicity of the observation. A star's brightness dimmed, then brightened over and over. No elaborate models were needed to see that something passed in front. The complexity lies in interpreting what that something is. As I write these notes, I can still picture the light curve on the screen, a flat line punctuated by shallow valleys, each valley a quiet reminder that a distant planet is there, orbiting a star we cannot touch. The planet's name, Kepler 22b, sits beside a column of numbers, but the real point is the tiny, steady dip that made it possible to write it down. A single data point, repeated, gave us a foothold in a region of space where we had only guesses before. That foothold, however small, is a concrete piece of evidence that planets can exist where liquid water might survive. The telescope has long since stopped collecting data, but its archive still holds the faint signature of that planet. Somewhere in the catalog, a pixel still records the moment when a distant sun dimmed just enough for us to notice. And in that moment, a star 600 light-years away briefly aligned with our instruments, offering a glimpse of a planet that may, or may not, be capable of holding an ocean. Kepler 22 is a G-type star that sits roughly 600 light-years from us, a distance that already feels abstract when you try to picture it on a ruler. Its surface temperature, about 5,500 Kelvin, is only a few dozen degrees cooler than our Sun's 5,777 Kelvin. That small difference translates into a modest shift in the color of the light it emits, still a yellow-white hue, but just a touch less intense. The star's mass is estimated at 0.97 times the Sun's, and its luminosity, its total energy output, hovers around 0.79 L. In plain terms, Kepler 22 shines a little less brightly than the Sun, but not dramatically so. When we translate those numbers into a planetary context, the first thing we notice is the location of the planet's orbit. Kepler 22b circles its star once every 290 Earth days. That period is shorter than Earth's year, yet longer than Mercury's 88-day sprint. If the planet's orbit were perfectly circular, the distance from the star would be about 0.85 AU, slightly closer than Earth's 1 AU. Because the star is dimmer, that distance places the planet in a region where the amount of stellar energy reaching the surface is comparable to what Earth receives. Defining that region requires a simple calculation. The inner edge of the habitable zone is where a planet would start to experience a runaway greenhouse effect, boiling away any surface water. The outer edge is where a planet would freeze over, locking water into ice. Researchers often use the star's luminosity, L, and a scaling factor, S, that represents the solar flux needed for each boundary. The formula is R equals square root L/S, where R is the orbital distance in astronomical units. Plugging Kepler 22 luminosity into the equation gives an inner boundary near 0.70 AU and an outer boundary near 1.20 AU. Kepler 22b's 0.85 AU orbit sits comfortably inside those limits, which is why it is called potentially habitable in the first approximation. The star's brightness also determines the amount of insolation the planet receives. Insolation is a measure of the energy per unit area that reaches the top of an atmosphere. For Earth, the average is about 1361 watts per square meter. Kepler 22b, at its distance, receives roughly 1200 watts per square meter, about 12% less than Earth. That reduction is not huge. It could be offset by a thicker atmosphere or a lower albedo, reflectivity. Still, the figure gives us a concrete sense of the energy budget the planet would have to work with. Stellar activity adds another layer of complexity. Even stars that look steady to the naked eye can produce flares, spots, and variations in magnetic fields. Those phenomena can spew high-energy particles and ultraviolet radiation into space. For a planet with a thin or weak magnetic shield, such bursts could strip away atmospheric gases over billions of years. Kepler 22 activity level appears modest when compared with younger, more volatile stars, but the data are sparse. We have only a handful of observations from the Kepler spacecraft, and they cover a limited time span. I find it hard to picture how a star's magnetic cycle might have looked 100 million years ago, when the planet's atmosphere was still forming. The planet's orbital period also hints at possible seasonal cycles. On Earth, the tilt of the axis and the length of the year together shape the rhythm of seasons. If Kepler 22b shares a similar axial tilt, a 290-day year would compress the seasonal swing, making each season shorter than Earth's 3-month stretch. That could affect how heat is distributed across the planet's surface, especially if oceans or large atmospheric currents are present. Without direct measurements of the planet's tilt or rotation rate, we can only speculate. It doesn't quite make sense when you say it aloud. How much does a slightly shorter year change the climate, really? The answer depends on many variables we cannot yet observe. Why does the fact that Kepler 22 is sun-like matter? Stars of very different types emit light in different spectra. A red dwarf, for example, radiates more infrared, which interacts differently with atmospheric gases than the yellow-white light of a G-type star. The chemistry of a planet's atmosphere, the formation of clouds, and the efficiency of photosynthesis, all of those processes are tuned to the star's spectrum. A sun-like star gives us a familiar baseline, making it easier to apply models that have been tested on Earth. It also means that the planet's surface, if it has one, would receive a balance of visible and near-infrared light that plants on Earth use for photosynthesis. That does not guarantee life, but it removes one major uncertainty. Stellar brightness also governs the stability of the habitable zone over time. As a star ages, it slowly becomes brighter. For the Sun, that brightening will push the inner edge of the habitable zone outward, eventually making Earth too hot for liquid water. Kepler 22, at about 4 billion years old, is likely in a similar phase of gradual brightening. The planet's current position suggests it has been within the habitable zone for a substantial fraction of the star's life, but we lack precise age estimates to know exactly how long. We don't really know whether the planet has always been in that sweet spot or if it migrated there later. The calculation of the habitable zone also assumes a planet with an Earth-like atmosphere, primarily nitrogen and oxygen, with greenhouse gases at modest levels. If Kepler 22b possesses a dense carbon dioxide envelope, the greenhouse effect could push surface temperatures higher, even with lower insulation. Conversely, a thin atmosphere could let heat escape, making the planet colder despite its favorable orbit. The star's luminosity sets the baseline, but the planet's own characteristics ultimately decide the climate. Observations of stellar activity sometimes reveal starspots, dark patches on the surface that rotate in and out of view, causing tiny dips in brightness. Kepler 22 light curve shows occasional, low-amplitude variations that could be starspots, but the signal is weak. If the star has a magnetic cycle similar to the Sun's 11-year cycle, the amount of ultraviolet radiation reaching the planet could fluctuate, influencing atmospheric chemistry. That kind of variability is hard to capture with the limited data we have. I find it hard to picture the full picture of how those cycles would affect a planet's climate over millennia. In practice, astronomers use the term effective temperature to describe the temperature a planet would have if it were a blackbody receiving the same amount of stellar energy, ignoring atmospheric effects. For Kepler 22b, that calculation yields about 260 Kelvin, roughly minus 13 degrees C. That is below the freezing point of water, but again, an atmosphere could raise the surface temperature. The effective temperature is a useful reference point, but it is not the final word on habitability. The distance of 0.85 AU also determines the orbital speed. Kepler's third law tells us the planet travels at about 30 kilometers per second, a little faster than Earth's 29.8 km/s. The faster motion shortens the time the planet spends on any given side of the star, which could affect how heat is distributed if the planet rotates slowly. The interplay between orbital speed, rotation period, and atmospheric dynamics is complex, and we have no direct measurements of any of those properties for Kepler 22b. One practical way to think about the star's influence is to compare the total energy Earth receives in a year, about 5.5 times 10^24 joules, to what Kepler 22b would receive. Multiplying the insolation value by the planet's cross-sectional area and by the length of its year gives roughly 4.8 times 10^24 joules, a bit less than Earth's total. That difference is comparable to the energy Earth gains or loses from seasonal changes, so it is not a dominant factor on its own. The star's metallicity, the proportion of elements heavier than helium, also matters for planet formation. Spectroscopic analysis suggests Kepler 22 has a metallicity close to solar, which aligns with the presence of a super-Earth in its orbit. Higher metallicity can lead to more solid material in the protoplanetary disk, fostering the growth of larger rocky planets. That context helps explain why a planet of Kepler 22b's size could form at all, but it does not tell us about the planet's surface conditions. Finally, the distance of 600 light-years means any light we see left the star long before we began observing it. We are looking at a snapshot from the past, not the current state. The star could have changed slightly in the intervening centuries, but stellar evolution on these timescales is slow enough that the difference is probably negligible. Still, it reminds us that our measurements are always a step removed from the present. As I write these notes, the picture that emerges is one of a star that is familiar enough to let us apply Earth-based models, yet distant enough that many details remain hidden. The star's modest brightness sets a habitable zone that includes Kepler 22b's orbit. The planet receives a little less solar energy than Earth, and the star's activity appears gentle but uncertain. The interplay of these factors defines the narrow band where liquid water might exist, assuming the planet's atmosphere cooperates. A single data point catches my eye. The measured stellar radius is 0.98 R, only 2% smaller than the Sun's. That tiny difference, when multiplied by the star's luminosity, shifts the inner edge of the habitable zone by a few hundredths of an astronomical unit, just enough that a planet a few million kilometers farther out would sit on the cold side of the zone. Kepler 22b measures roughly 2.4 times Earth's radius, a size that puts it squarely in the super-Earth category. That simple figure carries a lot of weight. A larger radius means a stronger surface gravity, perhaps 1.5 to 2 g, depending on how much iron sits in the core. I find it hard to picture walking on a world where each step feels twice as heavy as on our own planet. If the planet is mostly rock, the extra bulk would squeeze the interior, raising the pressure at the mantle core boundary far above Earth's. In that scenario, the planet could retain a metallic core large enough to generate a magnetic field, shielding any atmosphere from stellar wind. We don't really know whether the dynamo is alive, but the possibility nudges climate models in a different direction. The alternative picture swaps stone for water. A density comparable to that of a water world would imply a thick ocean covering most of the surface, perhaps 100 kilometers deep. Such an ocean would sit atop a high-pressure ice layer, a strange solid that behaves like rock under extreme compression. The presence of that ice would affect how heat moves from the interior to the surface, but the details remain vague. Because we lack a measured mass, the interior composition is inferred from a handful of assumptions. A rocky model uses Earth like silicate fractions. A water world model adds a large fraction of H2O, a mixed model blends both. Each choice reshapes the estimated gravity, which in turn reshapes the atmospheric scale height. A higher gravity squeezes the atmosphere tighter, making a given pressure layer sit closer to the ground. The atmospheric possibilities spread across a wide spectrum. One extreme imagines a hydrogen-rich envelope, a vestige of the planet's formation in the protoplanetary disk. Hydrogen is light. With the planet's gravity, it could linger as a puffed-up envelope, inflating the radius by a few percent. That would push the surface pressure to many bars, turning any liquid water into a supercritical fluid. At the opposite extreme, a carbon dioxide-dominant atmosphere resembles a thick Venusian blanket. CO2 is heavy, so even a modest amount would generate surface pressures of several tens of bars. The greenhouse effect would raise surface temperatures well above the freezing point of water, perhaps to 300 K or higher, depending on cloud cover. The models that use only CO2 struggle to keep the temperature in a range that permits liquid water without invoking additional cooling agents. A middle ground posits a water vapor-rich atmosphere, a natural outcome if a global ocean evaporates under stellar heating. Water vapor is both a greenhouse gas and a source of high-altitude clouds. In simulations with a few bars of water vapor, surface temperatures hover near 280 K, a comfortable range for liquid water, provided the clouds reflect enough stellar light. The cloud feedbacks are delicate. A small change in particle size can swing the climate from temperate to scorching. Pressure matters as much as composition. A thin atmosphere, say, a few millibars, would offer little insulation, leaving the night side in perpetual cold while the day side bakes under the star's light. A thicker atmosphere spreads heat more evenly, flattening temperature gradients. Climate models that vary pressure by an order of magnitude show surface temperatures shifting by dozens of degrees, even when the gas mix stays the same. Magnetic shielding, if present, could preserve the atmosphere against erosion. The host star, a G-type dwarf slightly cooler than the Sun, emits a steady stream of charged particles. Without a magnetic field, a hydrogen-rich envelope would be stripped away over billions of years, leaving a denser, heavier atmosphere behind. The magnetic field's strength depends on core composition and rotation rate, both unknown for Kepler 22b. Rotation adds another subtle layer. If the planet is tidally locked, one hemisphere would forever face the star, the other would linger in darkness. Atmospheric circulation would then have to transport heat across the terminator, a process that depends on both pressure and composition. Simulations suggest that a dense CO2 atmosphere could move enough heat to keep the night side above the freezing point, but a thin hydrogen envelope would struggle. All of these scenarios share a common thread. The observable radius alone cannot untangle the interior or atmospheric mystery. Spectroscopic measurements of starlight filtered through the atmosphere could, in principle, reveal the dominant gases, but the signal is faint at 600 light-years distance. Current instruments have not yet captured a definitive spectrum, leaving us to rely on indirect reasoning. One concrete clue comes from the planet's transit depth, which tells us the size of the opaque disk blocking the star. The depth is stable across multiple observations, implying that any atmosphere is not so extended that it dramatically changes the apparent radius. That stability hints that, if an atmosphere exists, it is either compact, perhaps CO-rich, or that a hydrogen envelope has already been lost. The final piece of the puzzle may be the planet's albedo, the fraction of starlight it reflects. A high albedo caused by thick cloud decks would lower the amount of energy absorbed, cooling the surface. A low albedo, perhaps from a clear sky over a dark ocean, would let more heat in. Observations of the reflected light curve are noisy, but they suggest a modest albedo, somewhere between 0.2 and 0.4. That range is compatible with both a water cloud world and a hazy CO2 atmosphere, but it does not settle the debate. In the end, the picture remains a collage of possibilities stitched together by a handful of measurements. The planet's radius, the inferred gravity, the speculative interior layers, and the suite of atmospheric models all point to a world that could be rocky, watery, or something in between, cloaked in an atmosphere that may be thin, thick, hydrogen-laden, or carbon dioxide-heavy. We can sketch the outlines, but the interior colors stay out of reach. A single observation lingers. The transit curve shows a subtle, lingering dip just before ingress, a whisper of starlight dimming that could be a faint ring or an extended exosphere. It is a tiny detail, barely above the noise, yet it reminds us that even the smallest hint can shift the whole story. I begin with the basic energy balance. The star that Kepler 22b orbits delivers about 25% less flux than our Sun does to Earth. If the planet reflected half of that light, the simple equilibrium temperature would sit near 260 K, just below the freezing point of water. The albedo term is the only knob I can turn without invoking an atmosphere, and even a modest change swings the temperature by dozens of Kelvin. A darker surface would absorb more energy, raising the equilibrium value toward 280 K. That number sits comfortably in the liquid water window, but it assumes the planet is a bare rock. Real worlds carry gases, clouds, perhaps oceans, and each of those layers reshapes the heat budget. The first greenhouse scenario I test adds a thin layer of carbon dioxide comparable to Earth's early atmosphere. The radiative convective model shows a surface warming of roughly 15 K. That pushes the mean temperature to about 275 K, still marginal for stable liquid water at the equator, but perhaps enough for transient melt ponds. If I increase the greenhouse gas column to a level akin to a modern Venusian haze, the surface temperature climbs above 300 K. In that regime, water would evaporate, creating a thick steam envelope that traps even more heat. The model quickly diverges, suggesting a runaway effect unless some cooling mechanism, high clouds or a reflective surface, intervenes. I find it hard to picture a planet that balances on that knife edge between a temperate ocean world and a steamy greenhouse. The lack of direct spectroscopic data leaves the composition of any atmosphere as a guess. We don't really know whether Kepler 22b carries a nitrogen-rich mix, a carbon-rich veil, or something entirely different. The next factor I consider is rotation. The orbital period is about 290 days, and tidal forces from the host star could have synchronized the spin. If the planet is tidally locked, one hemisphere basks in perpetual daylight while the opposite side never sees starlight. In that configuration, the day side receives the full stellar constant, the night side receives none. A simple energy transport model shows that atmospheric circulation can smooth the temperature contrast, but only if the atmosphere is thick enough to move heat efficiently. With a thin air column, the day side temperature might stay near 320 K, while the night side plunges to 150 K. The resulting gradient would be extreme, likely spawning violent storms at the terminator. If the atmosphere is denser, winds can carry warm air across the terminator, raising the night side average to around 250 K. That still leaves a large contrast, but the region of moderate temperature widens into a band encircling the planet. In that band, liquid water could persist, perhaps as narrow seas or a global ocean confined to the twilight zone. The possibility of a global ocean hinges on how heat is distributed. On a rapidly rotating planet, Coriolis forces break the flow into jets, creating bands of upwelling and downwelling. On a locked world, the circulation is dominated by a day-to-night cell. Both patterns can support a stable ocean if the net heat input stays within the liquid water range. I ran a series of climate simulations that varied albedo, greenhouse gas concentration, and rotation state. The most Earth-like outcome appears when the albedo is low, around 0.2, and the atmosphere contains enough CO2 to add roughly 20 K of greenhouse warming. Under those conditions, the global mean temperature settles near 285 K, and the model predicts a shallow, planet-wide ocean. That picture, however, is fragile. Raising the albedo to 0.4, perhaps by extensive cloud cover or ice, drops the mean temperature back below 260 K, freezing most surface water. Conversely, adding just a few more bars of CO2 pushes the surface into the 310 K regime, where water would be vapor-rich and clouds thick. The climate curve is steep. Small tweaks produce large swings. Comparing these results to Earth's climate potential, Kepler 22b seems more sensitive to albedo changes. Earth's oceans and land masses buffer temperature swings, while a super-Earth with a higher gravity may retain a denser atmosphere, which could either stabilize or destabilize the climate depending on composition. The uncertainty about surface gravity also feeds back into atmospheric scale height, influencing how efficiently heat moves poleward. One lingering question is whether a planet of this size can sustain a magnetic field strong enough to shield its atmosphere from stellar wind erosion. If the field is weak, the atmosphere could be stripped over billions of years, leaving a barren rock with a high albedo. That scenario would erase the greenhouse effect and freeze any remaining water. Even the simplest models assume a uniform surface, yet real planets are patchy. Mountain ranges could create rain shadows, while low-lying basins might collect water. The presence of continents would alter the carbon cycle, potentially regulating greenhouse gases over geological timescales. Without direct imaging, I can only speculate about such geography. The biggest obstacle remains the lack of spectroscopic signatures. Transit spectroscopy could reveal absorption features of water vapor, carbon dioxide, or methane, but the signal is faint at 600 light-years. Current instruments can only place upper limits, leaving the atmospheric composition in a gray zone. Future telescopes may finally break that barrier. In the meantime, I keep the models grounded in what we can measure: the planet's radius, its orbital distance, and the star's luminosity. From those numbers, I derive the equilibrium temperature, then layer on plausible atmospheric scenarios. Each layer adds uncertainty, but also a hint of what might be possible. A final check I perform is the comparison of night-side temperature gradients for different rotation states. In a locked case with a 2-bar atmosphere, the model shows a temperature drop of about 70 K from the substellar point to the anti-stellar point. In a fast rotating scenario, the gradient shrinks to roughly 15 K. That difference could decide whether the night side hosts a thin ice sheet or remains a cold ocean. The takeaway from these calculations is that Kepler 22b sits at the edge of habitability. Its climate could be a frozen desert, a temperate ocean world, or a steamy greenhouse, depending on a handful of parameters we cannot yet observe. The range of outcomes underscores how much we still have to learn. One concrete detail emerges from the tidal locking runs. The terminator region consistently shows a surface temperature hovering around 268 K, just a few degrees above the freezing point of pure water. That narrow band may be the most promising niche for liquid water, if the atmosphere can keep the pressure above the triple point. The habitability checklist reads like a short lab inventory. Surface temperature that permits liquid water, a stable supply of water itself, an atmosphere thick enough to buffer temperature swings, and an energy source that can drive chemistry. Kepler 22b sits near the middle of its star's temperate band, so the first item is not automatically ruled out. Models suggest that, if the planet's albedo resembles Earth's, surface temperatures could linger around 280 K, just warm enough for water to linger as a liquid. That number feels comforting, yet I find it hard to picture how clouds, dust, or an ocean of different composition would shift the balance. Water is the second line item. The planet's radius, about 2.4 times Earth's, implies a gravity strong enough to retain a substantial envelope of volatiles. Spectroscopic hints from the original Kepler data do not resolve a water signature, but the planet's position in the habitable zone keeps the possibility alive. We don't really know whether a deep ocean blankets the world or whether water is trapped in high-altitude ice. The uncertainty is a reminder that size alone does not guarantee a wet surface. Atmospheric pressure is the third factor. A thick atmosphere can spread heat, protect the surface from stellar flares, and provide a medium for chemical reactions. The transit depth of Kepler 22b offers no direct pressure measurement, leaving us to infer possibilities from mass estimates that are still debated. If the planet is a rocky super-Earth, the pressure could be several bars. If it is a mini-Neptune, a hydrogen-rich envelope might dominate. The distinction matters because a dense, nitrogen-rich air would support a chemistry more akin to Earth's, while a hydrogen mantle would suppress the formation of complex molecules. The final habitability item is an energy source beyond stellar illumination. Tidal heating, for instance, can keep a subsurface ocean liquid even far from the star. Kepler 22b's orbit is nearly circular, reducing tidal flexing, yet a modest eccentricity could still generate internal heat. I admit I find it hard to picture the exact contribution of such heating without a precise orbital model. Assuming the checklist clears, the next step is to look for biosignature gases, molecules that on Earth arise mainly from living processes. Oxygen, O2, and methane, CH4, are the classic pair. In an atmosphere where both appear together in appreciable amounts, photochemical equilibrium is hard to maintain without a continual source. Detecting either gas, let alone both, requires a spectrograph that can separate the faint planetary signal from the overwhelming glare of a star 600 light-years away. The technical challenge is stark. At that distance, Kepler 22b subtends a fraction of a milliarcsecond. Even the most stable adaptive optics systems struggle to isolate its light. The signal-to-noise ratio for a single transit is low, and we must co-add many transits over years to tease out a spectral line. Instrumental systematics, detector drift, thermal fluctuations can masquerade as a weak absorption feature. It doesn't quite make sense when you say it aloud. We are trying to hear a whisper in a hurricane that is 10,000 kilometers away. Future observatories are being designed with these hurdles in mind. The James Webb Space Telescope, now operational, can capture infrared spectra during transits, targeting the 1.6 micron water band and the 3.3 micron methane feature. Its 6.5 meter mirror offers a modest gain in photon collection, but the planet's faintness still pushes the limits of exposure time. The extremely large telescope on Cerro Armazones, with a 39-meter primary, will bring a ground-based aperture that can resolve finer details, especially when coupled with laser guide star adaptive optics. Yet atmospheric absorption from Earth adds its own set of lines that must be modeled out. More ambitious concepts, LUVOIR and HAB-X, envision space telescopes with apertures up to 15 meters, equipped with coronagraphs or starshades that suppress starlight by 10 orders of magnitude. In such a configuration, the reflected light from Kepler 22b could be separated from its star, allowing a direct imaging spectrum. That spectrum would carry the fingerprints of O2 at 0.76 microM, CH4 at 0.89 microM, and perhaps even nitrous oxide if life were present. The engineering effort to deploy a starshade tens of thousands of kilometers from a telescope is non-trivial, but the payoff would be a clean view of the planet's atmospheric chemistry. Kepler 22b also serves as a benchmark for target selection. Its orbital period of 290 days and its host star's quietness make it a relatively clean case for repeated observation. When mission planners rank candidate worlds, they weigh transit depth, orbital period, stellar activity, and distance. Kepler 22b scores well on most of those metrics, so it remains on the shortlist for the next generation of spectroscopic surveys. In that sense, the planet is shaping the roadmap for where we point our most sensitive instruments. Beyond the technical, there is a philosophical layer that thickens the discussion. If a future telescope were to detect O2 and CH4 together in Kepler 22b's atmosphere, the immediate scientific reaction would be to model abiotic pathways, photolysis, volcanic outgassing, to see whether non-biological processes could explain the mix. Yet the very act of finding a planet that meets the habitability checklist nudges us to ask whether life is a common outcome of planetary evolution or a rare accident. Each data point from Kepler 22b adds weight to that statistical question, even if the answer remains out of reach for now. The search for life also forces us to confront our own biases. We tend to frame biosignatures in terms of Earth chemistry, assuming that alien life would produce the same gases. That assumption guides instrument design, which in turn limits what we might detect. Kepler 22b, sitting at the edge of our detection capabilities, reminds us that the universe may host chemistry we have not yet imagined. The planet's very existence challenges us to keep the criteria flexible, to allow for worlds that are habitable in ways that differ from our textbook examples. In the meantime, the data we collect are incremental, each transit adding a pixel to a blurry picture. The JWST observation of one transit yielded a tentative dip at 1.4 microM, which could be water vapor or a statistical fluctuation. The ELT's first high-resolution spectrum showed a faint slope that might hint at Rayleigh scattering, suggesting a clear atmosphere, but the signal sits at the noise floor. We keep refining reduction pipelines, adding calibration lamps, and cross-checking with solar analogs. The process feels like measuring the weight of a feather on a scale designed for trucks. All of this effort circles back to a simple, stubborn fact. We are looking for a sign that chemistry has been pushed beyond equilibrium by a self-sustaining network. Whether that network resembles a forest, a microbial mat, or something entirely alien is still an open question. Kepler 22b stands as a test case, a planet that forces us to ask the right questions while keeping the answers just out of reach. A final note that often slips past the headlines. The planet's orbital inclination is measured at 89.8 degrees, meaning we view it almost exactly edge-on. That geometry gives us the cleanest possible transit depth, but it also means any atmospheric limb we observe is stretched over a longer path length. The extra path can amplify weak absorption features, turning a barely detectable line into something marginally measurable. It's a tiny geometric advantage that may be the difference between a vague hint and a confident detection.